Here are solutions to homework set number 11 for ECE 376. In this assignment, we're looking at filters in the S-plane and the Z-plane. The first problem is filters in the S-plane. Given a filter in the S-plane, what's the differential equation and what's the output given a sine wave input? So here, S means derivative, so cross multiply. S means the second derivative of y plus 4 times the first derivative plus 30 times y is 5 times the derivative of x plus 10 times x. B says find the output of the inputs a constant and a sine wave. And here we use superposition. What superposition says is that for linear systems, f of a plus b is f of a plus f of b. Use that. I'm going to treat this as two separate inputs. One is a constant, one's a sine wave. For constant input, here's the gain everywhere. All I care about is what's the gain at s equals 0 times the input at dc. Gives me 2. For sine wave input, this is the gain everywhere. What's the gain at 4 radians per second times the input at 4 radians per second. For the input, real part is cosine minus j is sine. So this means, or is represented as 0 minus j5. Multiply it all together, I get a complex number. Real part means cosine minus j is sine. The total answer then is DC plus AC. That's in the S-plane. In the Z-plane, pretty much the same answer. In the Z-plane, this is a difference equation. Multiply it all out, and what that means is the next value of y, or y2 samples in the future, plus 1.8 times y, one sample in the future, plus the current value of y, is equal to 0.01 times the next value of x plus the current value of x. So this is a perfectly valid difference equation. Some people prefer avoiding future values of y. So if I delay it by 2, just do a change in variable. This is the same thing, written slightly differently. Either equation is valid. If I want to know what the output is for constant and sine wave, again I use superposition. The DC term, s equals 0, z is e to the st, or 1. Here's the gain everywhere. What's the gain of DC? In the S-plane, I plug in s equals 0. Z-plane, I plug in z equals 1. Times the input, I get a number. When the input is sine 4t, s is j4, z is e to the st. It's a complex number. If you put your calculator in radians mode, you get this. For TI calculators need to be in radians mode for this to work. Otherwise, you get a domain error. HP calculators don't care. HPs work everywhere. Here's the gain everywhere. All I care about is what's the gain at 4 radians per second, or at the gain, 4 radians per second, times the input. I get a complex number. Output is, well, real part means cosine, minus j means sine. So here's the total answer. Problem 3 is come up with a filter with the same gain versus frequency. Here the conversion from the S-plane to the Z-plane is z is e to the st. T is 0.01, here's s. Plug it in, I get 0.96, 0.95, 0.94. So these these 3 poles in the S-plane correspond to these 3 poles in the Z-plane. To find the gain on top, match the DC gain. Plug in s equals 0, the DC gain should be 0.8333. Find k to have the same DC gain, and k is 0.000928. So here's g of z. And sometimes we'll add a couple z's in the numerator to match the phase shift. That doesn't affect the gain, just the phase. But that's a little more complicated than I want to get into. That's essentially the same filter, same gain versus frequency. And I can check that. If I plot g of s and g of z on the same graph, here's what I get. G of s is in red, or g of s is in blue, g of z is in red. Same gain versus frequency. It's the same filter. That's with real poles. If I have complex poles, same procedure. I've got a 0 at s equals 0 in the S-plane, put a 0 at z is plus 1 in the Z-plane. Poles at minus 2 plus minus j15 S-plane, put the poles at 0.96 plus minus j.14 in the Z-plane. So here's the filter. Pick k to match the gain somewhere. In this case, I can't use 0 because I get 0 equals k times 0, solve for k. Pick a frequency other than 0. I chose 15 radians per second, so g of s at 15 radians per second should be 7.48. Pick k so that g of z at the same frequency is also 7.48. And if you do that, you get k as 0.2932. Checking. Calculate the gain of g of s, calculate the gain of g of z, plot them, and I get the same curve. Same gain versus frequency means the same filter. And here you can also see it doesn't matter which frequency you chose. I pick k to match the gain at 15. If I pick any point, I've matched the shape, matched the gain at a point, I'll match the filter. Problem 5 says write a C program to implement that filter. So here the trick is multiply it all out, cross multiply, solve for the highest power, actually convert to a difference equation, do a time shift so it's no longer using future values, and solve for the current output. There's your program, and you can almost see it by inspection. The denominator polynomial shows up right here with a minus sign because I cross multiply and bring it left. The numerator polynomial shows up here. Decreasing powers of z are past values of y and past values of x. The code then is pretty much the same always. I remember the old inputs, remember the current input, or measure the current input, remember the old outputs, and here's your difference equation. Change that one line of code, I change the filter. This is one thing you can do with filters. Suppose I have an ultrasonic range sensor. If I'm measuring something at 100 millimeters, the measurement will be 100, and there's going to be a little bit of noise on it. Experimentally, the standard deviation was about 3. So this is kind of a fictitious way of creating range sensor data. If I take that data, create it in MATLAB, find the mean, find the standard deviation. Again, the mean's 100, standard deviation is 3. Yeah, no surprise. The 90% confidence interval would be when I go from the mean plus or minus 1.64 standard deviations. 90% of the time, I'll get a reading between 104.9 and 95.1. So that's what my raw data looks like. If I take that data and run it through an FIR filter, just take the average of the last 5 data points, that is a filter. It's not a very good one, but it is a filter. I can do that in MATLAB. Y is just the average of the last 5 data points. I've got a mean, standard deviation. Same mean, still 100. Standard deviation now is smaller. It was 3, it's now 1.3. And what it should do is when I take the average, it should drop by 1 over square root of 5. So take 3, divide by square root of 5, that's roughly 1.38, which checks out. If I then plot the data, or I want to find the 90% confidence interval, the next measurement, or filtered measurement, should be the mean plus or minus 1.64 standard deviations, should be between 97 and 102. So taking the average does help. It gives me a better measurement, less noise. You can do better. For example, if I took a second order Butterworth filter with poles at plus minus J2, here's the same filter in the z-plane. This is how I implement it. That's how I analyze it. The way I implement it is I'm going to say at each data point, I'll take the current value is 1.96 times the previous value, minus 0.96 times the value 2 samples ago, plus 0.00008 times the input. If I do that throughout all the data, I still have a mean of 100, but now the standard deviations drop from 3 down to 0.26. So I have a much better idea of what the actual distance is going to be. And if I plot the data, that helped get rid of a lot of the noise. That's what filtering does for you. I can take a noisy measurement, get rid of the noise, and get a much better measurement. Taking the average is a filter. Not a very good one, but it is a filter. I can do much, much better using z-transforms. So that is homework set number 11 for 376.